About MapReduce. In this module, we'll discuss how MapReduce can be used to process large volumes of data stored in a Hadoop cluster. We'll talk about the MapReduce architecture and infrastructure. We'll talk about fault tolerance in MapReduce. By example, we will describe how a MapReduce job works. We will talk about running MapReduce jobs, and we will conclude this module with a lab exercise, providing an opportunity to apply some of the concepts that we have discussed. What is MapReduce? MapReduce is a programming model for processing large volumes of data. It's processed using record-oriented data processing. Those records consist of key and value pairs. The main goal of MapReduce is automatic parallelization and distribution of the tasks in a MapReduce job. Ideally, each node processes data stored locally on that node. The MapReduce process incorporates two developer-created phases. One of them is the map phase, which basically reads blocks and performs filtering and sorting type operations. And there is the reduce phase, which performs summary operations, calculates final results. Between the map and reduce phases is a phase called sort, shuffle, and merge, which sends data developed and generated by the mappers to the reducers for final results. MapReduce programs are generally, but not always, written in Java. Other language support is available using what is referred to as Hadoop streaming. The MapReduce framework abstracts all housekeeping requirements from the developer. That is nice in that the developer only needs to worry about writing a MapReduce program that answers a specific question about the data it's being run against. As you will see, MapReduce is fault tolerant as well. Let's talk about the MapReduce architecture. There are actually two MapReduce architectures, MapReduce version 1, referred to as MRV1, and MapReduce version 2, which is referred to as MRV2 or YARN. Both manage compute resources, jobs, and tasks. The API for either is the same. MRV1, MapReduce version 1, is in production and is proven and is solid implementation. MapReduce version 2 is a much newer framework to leverage YARN. YARN is just yet another resource negotiator. And the primary purpose for YARN is to allow for large clusters to scale beyond the 4,000 node range. Let's take a moment and discuss the similarities and the differences between MapReduce version 1 and MapReduce version 2. Any jobs are typically submitted through a client of some sort. That could be a terminal window, that could be a Java application, for example. In MRV1, a single master, known as the job tracker, manages the scheduling and the generation of resources for each and every job submitted to the cluster. The job tracker manages each and every job through its entire life cycle. On the data nodes, there are task trackers, one task tracker daemon on each data node. The job of the task trackers is to simply run tasks, whether they be map tasks to read blocks of data stored in HDFS, or reduce tasks to aggregate the data generated by the map tasks. And of course, MRV1 takes advantage of data stored in the distributed file system, HDFS typically. MRV2, on the other hand, uses a resource manager as opposed to a job tracker. And the job of the resource manager is to, much like the job tracker, manage the scheduling and the allocation of resources for the jobs themselves. However, the resource manager does not manage a job through its entire life cycle. That responsibility is pushed down to a daemon that runs on the data nodes called the node manager. The node manager coordinates the running of a job and then coordinates that job through its entire life cycle. The application master in MRV2 performs a similar task to the task tracker in that it is the responsibility of the application master to run, map, and reduce tasks against the data that is, again, typically stored in HDFS. Let's take a moment and look and see how a MapReduce job is processed. The job is initiated through a client application. A job ID is made to the job tracker master for that particular job. At the same time, the client pushes down the jar file containing the classes required for that particular MapReduce job, as well as the configuration items required to process this job. The job is submitted from the client to the job tracker. The job tracker then initializes the job and determines how many blocks need to be read from HDFS and how many tasks need to be created to read those blocks. The job tracker will tell the task tracker on a particular data node that it needs to create an instance of a map task or a reduce task. The task tracker on the data node will reach out to HDFS and pull back the appropriate class, whether a map class or a reduce class, that it has been instructed to run. It will then launch that task in a child VM and run that MapReduce task until its completion. Now let's take a look at running a MapReduce job managed by MapReduce version 2.0. Again, a job is submitted through the client application and a request for a new application is made to the resource manager. At the same time, again, a copy of the jar file containing the Java classes that need to be available to run this job are pushed down to HDFS, as is the configuration. The job is submitted to the resource manager, at which point in time a new container is generated called the node manager on one of the data nodes. The node manager will then launch the MapReduce application master. The application master will then initialize the job and determine how many blocks of data need to be read from HDFS for running this particular job. The resource manager will ask to resource allocation at this point in time, and the application master will start a new container on a different data node to run the map task or the reduce task that is directed to run. The node manager will launch a yarn child. The yarn child will then reach back to HDFS and extract the mapper or reducer class and then instantiate that class and run it on that particular data node. Let's talk about fault tolerance in a MapReduce program. Tasks processed periodically sending heartbeats up the chain to the master, whether it be a job tracker master or a resource manager master. Any task that fails to heartbeat during a particular period is presumed to be dead, and that task's JVM will be killed. A task that throws an exception is considered failed, and tasks that have failed are rescheduled on the system, but not necessarily in any particular order. It's ideally going to be restarted on a different node than it failed on. If a particular task, a mapper or a reducer, fails 4 times, then the job will be considered failed. How does MapReduce work? Every MapReduce job has inputs or blocks of data that the MapReduce job is going to be run against. And every MapReduce job will consist of tasks. Again, those tasks or units of work, will be either mapper tasks or reduce tasks. And a job can have any number of map tasks and any number of reduce tasks. There are no fixed set numbers. Map tasks read input splits or blocks of data, and from the input data generates what is referred to as intermediate results. Those intermediate results are then passed to a reduced task or reduced tasks as may be, and those reduced tasks generate final results or basically aggregate the data from those intermediate results. A job is submitted from a client as noted earlier. The job does get assigned a job ID. The number of input splits or blocks that need to be read will be determined. Then the client will make sure that the jar file and the configuration items are copied to HDFS for sharing between the data nodes. A map task is created for each input split or block that needs to be read. Periodic heartbeats between the slave data nodes and the master nodes occur, and these heartbeats are used to identify the readiness and availability of resources on the slave node to execute tasks. The master node, whether it be a job tracker node or resource manager node, assigns tasks to slave nodes that have available capacity. A JVM is instanced on the slave and the task runs in that JVM. This means that every task will run in relative isolation from any and all other tasks running on that data node in the cluster. Task status, as far as progress, etc., is periodically sent from the data node through the task tracker to the master node. Let's identify some very important thought keys before we proceed. A mapper or mappers processes basically process a single record at a time, and after the processing of that record is completed, it will emit a key and a value pair for each record that was read. The intermediate key value pairs that are generated by the mappers become the input to the reduce tasks. The reduce tasks aggregate the intermediate keys from the mappers and generate final output. Let's take a look at a simplified version of MapReduce. Here we have 3 nodes. Each of the 3 nodes has 7 blocks of data that needs to be read that are stored on those nodes. As such, there will be 7 map tasks instantiated on each of the 3 data nodes. 1 map task to read 1 block of data. Each of the map tasks will emit intermediate data, and that intermediate data will be stored locally on the node that it is generated on. There may be as many intermediate data files as there are blocks of data to be read. There be more, there may be fewer. There could be 0 intermediate data files generated. After all of the blocks have been read by all of the map tasks across all of the data nodes, then the key and value pairs from the intermediate data files will be shuffled across the system utilizing network bandwidth to the nodes where the reduce tasks are going to run. Those intermediate data files will become the input to the reduce tasks. The reduce task will read each of the inputs, a key and a value pair, and generate final results, storing those final results to HDFS. As you can see, MapReduce is not all that dissimilar to a Unix pipeline, where you can have input that you search for specific information from, sort that data, aggregate it, and then generate a final output. If we take those thought keys mentioned a bit earlier and expand on them here, each map processes a single input split or block of data from HDFS. The framework passes one record at a time, which will be a key and a value pair, to the mapper. The mapper will write intermediate data in the form of key value pairs to local disk. During the sort, shuffle, and merge process, all values for the same intermediate key are transferred to the same reducer for aggregation. The reducer is passed each key and an iterator of values, or an array of values. The reducer will process that array of values and generate output, which is written to HDFS. Files stored in HDFS can be of many formats, whether it be text, binary, JSON, sequential, etc. The format of a file must be specified in the configuration of the job so that the record reader knows how to read key value pairs of that format from the block of data it is going to read. The record reader will extract a key value pair in that particular format from the block and pass it to the mapper. The mapper will then process that key value pair and generate intermediate results in the form of key value pairs. This process ideally will be taking place in parallel, many mappers on each node across all of the nodes in the cluster. Once the mapping processes are completed, then if there is but one reducer for the job, then all keys and all values for those keys will be passed to the node where that single reducer is running. However, if there are multiple reducers running, then the partitioner will ensure that all the values for a particular key get shuffled to the same reducer. The reducer will then use this intermediate data as its input, again in the form of a key and a value, but the value now is an iterator or an array. The reducer will process all the values in the array, generating a final answer associated with all of those values. And then the reducer will read the next key value pair from intermediate data and aggregate that data as well. Once the job is completed, then all final results will be stored in HDFS. So with the things we have talked about firmly in mind, let's take a look at a pretty simple example that really is very descriptive of how MapReduce actually works. We will use word count to describe how it works. Okay? It is the hello world, if you will, of MapReduce. For purposes of this example, assume that we have a text file that is less than 128 megabytes, which means all the text is in one block. The key in the key value pair is going to be the byte offset into the file for a particular line of text. And the value, of course, is going to be that line of text. So if we take a look at pseudocode for this, we can see that the input to the mapper is a key, byte offset, and a value, a line of text. And in a simple for loop, we just simply say for each word in value, output the word itself as the key and literal 1 as the value. So read in a key value pair. Notice we basically eliminate the key. We don't use it. We replace it in the output statement. We read the first record, eliminate the key, loop through each word in the value, and output each word and the number 1 as the key value pair emitted by the mapper. So imagine that the input to our mapper is simply these 3 lines. 2120 is the key and the byte offset to this line of text in the file. See the quick brown fox jump over the lazy dog. And 2166 is the byte offset to the second line in this file, and 2202 is the byte offset to the third line in this file. Taking a look at the Java code for the word count mapper, we can see that the word mapper class has 4 arguments: a long writable and text objects, which are the input key and value to the mapper, and a text object and int writable, which are the output values for the key and the value pair from the mapper. You see that the map method takes a text object and an int writable object. Okay, the long writable is a key, the text value is the line to be processed. It also accepts and called an output collector object, which is for writing out the key and value pair to intermediate data. The value input is a text object, which means it has to be converted to a string before we can do anything with it. So we convert the value to a string variable called s, and then we just simply loop through that string, identifying each word in the string and outputting a text object, which is the word, which is going to be the key, and outputting a int writable object, which is the value, the literal 1. So we output the word, as we saw earlier, and the value 1 associated with that word. The intermediate data output by the mapper would look something along these lines. If we look back at the input data, we would see that the first sentence is, see the quick brown fox jump over the lazy dog. C and 1 is the output for the first line. The and 1 is the output for the first line, the second word. Quick and 1 is the output for the first line, the third word, etc., etc. The shuffle process is basically the way that the intermediate data files generated by a mapper or mappers are fetched by the reducer or reducers. The shuffle process does have activities that occur on both the map and the reduce side of the process, and this should be totally transparent to all of us as it is part of the infrastructure. That is, of course, until it becomes slow or maybe something actually goes wrong. As far as shuffle and the activities that take place on the mapper side, mapper output is generally written to a circular memory buffer. When that buffer is nearly full, it's prepared for write. The key value pairs that have been generated by the mapper are placed in an appropriate partition. The partition contents themselves get sorted by key, and then a new spill file is generated on the local file system. The spill files will get merged together if there are more than one of them. And the resulting output file, or files if there are more than one, are marked as available. Here we see some of the many configuration items that can be used to tune the map side portion of sort, shuffle, and merge. The sort, shuffle, and merge activity that takes place on the reduce side consists of a reducer or possibly multiple reducers polling a job tracker or resource manager asking for input locations. Once the input locations for intermediate files are identified, the reducers copy those intermediate files that were generated by the mappers from whatever locations they're in to the node where the reducer is running via HTTP. These inputs are held in RAM until certain thresholds are reached, at which case they're spilled over to disk. Files from the various mappers get recursively merged, and once all of the intermediate data files have been merged, then the reducer code is actually invoked. Here we see some of, again, the many configuration items that control reduce side activities in the sort, shuffle, and merge activities. If you recall, the output from our mapper was a key, the word itself from the input, and a value, the literal 1. All of the key value pairs emitted from the mapper were then shuffled to the node where the reducer would run and collectively merged into key value pairs. However, the value is now a Java iterator. So for example, the key word A has 2 ones associated with it, which indicates that the word A showed up 2 times in the input stream, as did the word jump, as well as quick. The words boxer, boxing, brown, etc. each have an iterator with a single 1, indicating that each of those words occurred once in the input data. The word the, however, as you can see, has 4 ones associated with it, indicating that the word the showed up 4 times in the input stream. And then, of course, the results that are to become input to the reducer are sorted in key sort order, A through W in this case, A to wizards. So this is what the input to the reducer would look like in this particular example. The reducer for word count is going to accept 2 arguments. The keyword, which of course is the word itself, and a Java iterator, which is going to be an array of ones, each one indicating how many times that word showed up in the input text. So as you can see, we are going to loop through the iterator and just accumulate the number of ones that are in the array. Then we're going to output as a final result the word itself and the aggregate of ones that are in the array. Here we look at the reducer code for the word count program. You can see the SumReducer class has 4 arguments. A text object, which is the input key, as well as an int writable, which is the input value to the reducer class, and a text object, which is the output key, and an int writable, which is an output value from SumReducer. And the reduce method itself takes a text object, which is the key, and the iterator, which is an int writable, as well as the output collector for writing final output with. And as you can see, we just simply loop through the iterator, okay, summing the values in the iterator, and then outputting as final results the key, which is going to be the word, and an int writable, which is going to be the aggregate of all of the values in the iterator. And the final output for word count would be written to HDFS and to a file that you could then look at, and this would be the result where you have A, and now instead of 2 ones, you have the aggregate of the number of ones that were in the array. And you have the word the, and instead of 4 individual ones, as we saw earlier, you would have the aggregate of the number of ones in the array. The third component of a MapReduce job is the driver component. The driver is supplied by the MapReduce developer and provides all of the details required for this job to run successfully. Here you see an example of the WordCount driver. The driver requires 2 input arguments. One, the input directory containing the data for this MapReduce job to run against, and an output directory to write final results to. Notice that you can give this job name or assign a job name for this job. You can use the set input paths and set output path methods to specify the input path for the data for this MapReduce job and the output path for the final results. Set mapper class you use to identify the Java class for the mapper. Set reducer class you use to set the Java class for the reducer. Set map output key is used to identify the data type for the output key, and set output value class is used to identify the data type for the output value from the mapper. Set output key class identifies the data type for the output from the reducer, and set output value class specifies the data type for the output value from your reducer. How do you run a MapReduce job? The developer must create a mapper and a reducer class, as well as the driver class, which we have seen examples of previously. The mapper, reducer, and driver classes must be compiled. Once compiled, one must create a jar file containing the compiled mapper, reducer, and driver classes, and then the job must be submitted using the Hadoop jar command. Now we have a lab exercise to give you an opportunity to apply some of the things that we've talked about. What you're going to need to do first is load some data into HDFS, which will be your source data. A mapper, reducer, and driver have been created for you to run word count against the data you're going to load into HDFS. However, you need to compile the Java code, create the jar file, and then submit the jar file to the cluster. Once completed, you need to then go take a look at the results and ensure that the word count job actually did aggregate the number of words and how many times each word showed up in the input text.